Okay, if the pressure in a canister is 9 atm and there are two gases, one's helium and one's argon, and argon is providing 3 atmospheres of pressure, how much is the helium provided? So if my total pressure is equal to 9 atm, and my total pressure in this case is going to be the pressure of the helium, or what is it, argon? The pressure of the argon plus the pressure of the helium, and I know that my argon is providing 3 atmospheres. And my total pressure is 9 atm. Then this is a Dalton's Law one, and we said Dalton's Law ones are pretty easy, so what's your answer here? So your answer here is 6. So that 6 atm is what must be provided by the helium. Okay, so now using the same canister, and what I know, there's about 40 grams of argon in the container. Can you tell me about how many grams of helium there are? Did you say 70? Definitely not 70. Double what? I like that you knew it was double, but double the grams? Double the moles. So why is this helium providing 2 times the pressure? There's twice as many of them. That's the only reason, because they're in the same container. The container is obviously the same size and the temperature is the same. So the only reason helium is providing twice the pressure is because there's twice as many heliums. So what you would need to do in this next problem is, I'm saying there's about 40 grams of this, and the number is about 40 grams of argon is 1 mole of argon. So there's about 1 mole of argon in that container. So how many moles of helium are in that container? 2. And I know it's 2 moles of helium because it's providing twice as much pressure as the argon. So there's twice as many of them. So then if you know that there's 1 mole, of argon, then there must be 2 moles of helium. So where'd that 40 grams of argon come from? Off the periodic table. Okay. What do we got for the next one? What do you want to do? Convert to Kelvin. As soon as you see temperatures, just 273, 300 K, 273, 405. Okay. All right, so I've got a gas. It occupies 900 milliliters. I want to know what the volume is at this new temperature. So I'm going to start off by writing my 900 milliliters here because my answer needs to be a volume unit, so that's got to be milliliters. So I've got 2 temperature units, 2 Kelvin units, and I need both those things to cancel out. So I have to put 1 in the numerator and 1 in the denominator. So what happened to the temperature? The temp went up. And if I was a gas and my temperature went up, what would happen to my size? I would get bigger. I would expand. So I got hotter, I expanded. So I need those 2 numbers to cancel out, but give me a bigger number than 900. So I'm going to put 405 up top, and I'm going to put 300 in the bottom. And so I've got 900 times 405 divided by 300. I've got 1215, and it looks like 1220 milliliters for sig fix. Why are you shaking your head, Destiny? What part? Yeah. Yeah. Yep. Right there. So I got 300 for the 20. The 27 turned into 300, and the 132 turned into 405. Okay, Jake. Why do you think, where's the 700 you're reading?
It's a two. It's a two. That looks like a 7. It's 12. It's 1220.
Okay, I'm sorry.
The one
So you round up.
So we only have 3 sig figs.
is.
So let me get rid of all this. And so your answer is going to be 1, 2, 2, 0 milliliters, right? That gives us 3 sig figs.
So always if you like that, we're always going to want to Kelvin.
Every single time I see a temperature unit for these gas law problems, I have to convert it into Kelvin because the what was our reasoning? Yeah, Celsius can give us negative numbers, which would give us like negative volumes and negative pressures, and that those can't exist. So because we go to Kelvin and the Kelvin doesn't have any negative numbers, it just goes to 0. Determine the pressure change at a constant volume of gas, 1 atmosphere heated. Okay, so kind of the same problem, right? 273, 273. So 311 K, then 199, yeah, 2 K. So my initial temperature is 291 and my final temperature is 311. And what I'm doing is I'm wondering what the new pressure is going to be, and I start off with 1 ATM. So if I work this 1 ATM, and I need a pressure, so this has got to be ATM out here, and I've got Kelvin and Kelvin, and the temp went up. So what would happen to the pressure of the container if the temp went up to this gas? The pressure would go up. So for this kind of problem, you should be thinking about throwing like a aerosol can into a campfire. I mean, don't do that, but the pressure would go up because it would explode. We don't want that. So I'm going to put 311 in the numerator and 291 in the denominator, and I'm going to get 311 divided by 291 times nothing. All right. Maybe if I could. .07 to 3 sig figs. Yeah. All right. So my new pressure would be 1.07 atmospheres. Final volume of a 200 milliliter sample of gas that's subjected to a temp change and a pressure change. Okay, so my temp change, 273, so I'm getting 283 as my initial temperature, and then 273, 8434 K. So here's my initial temperature and my final temperature and my initial pressure and my final pressure, and I start off at 200 milliliters. So I'm going to start with 200 milliliters. Let's do the temperature first. So if I'm a volume of gas and I'm a particular size and my temp goes up, what would happen to my size? I would get bigger. So I'm going to take my two temperature numbers, my 348K and my 283K, and set them up like this so the K's cancel out and that the number 200 gets bigger when I do the math. And then I've got a pressure that goes from 550 to 860. So if I'm a volume of gas and the pressure that's exerted on me goes up, what would happen to my size? No. I'm a gas. I'm absolutely susceptible to pressure changes. So I get smaller. I am a volume of gas and stuff pushes on me harder. What do? I shrink, right? I take a basketball into the swimming pool with me and dive down to the bottom. What happens to the basketball? the basketball gets smaller. What happens to you when you dive down into the bottom of the swimming pool? I mean, do you not feel like yourself that you're being crushed? So what do you think is happening to your body? The pressure increases, so what do you think happens to the size of your body? You get crushed. You are smaller. At the bottom of the swimming pool, you are a smaller volume person. Absolutely. You have air inside of your blood vessels. You've got air inside of your lungs, and all of that stuff gets smaller. It gets crushed. So this would make this smaller. So I'm going to take my 550 number and put it in the numerator, and my 860 number and put it in the denominator, because this pressure change should make this thing get smaller. So these two things are fighting each other. Not a big deal. 200 times 348 divided by 283 times 550 divided by 860. 112.1. I got 3 sig figs, so 112 milliliters. So in this case, the pressure change wins out, which makes sense because the pressure change was much larger than my temperature change was. Do we want to talk about that one again? Okay, I understand. So what I want you to be thinking about is, I have this gas and it's this 200 milliliters. And these things, this pressure change and this temperature change, those are things that are acting on the gas. So I am modifying these things. So the way I would think about them is, I've got a balloon, and this balloon is at 200 milliliters. So we know how big 200 milliliters, it's not very big. And so I take this balloon, and what's the first thing that I did to my balloon? I heated it up. So what did my balloon do? It got a little bit bigger. Okay, great. So I wrote my temperature fraction like this. Why? Because this number divided by this number makes that number a bigger number. So that's why I set that up like that. Okay, so now I've got a balloon that got a little bit bigger, and now what I'm going to do is the thing was sitting at 550 millimeters of mercury, and now I increase the exterior pressure to 860. So I got this balloon that was 200 milliliters, it got bigger, and now the outside pressure starts pounding on it. So what does the balloon do? It shrinks back down. That's how I would like you to think about this. So when you're looking at these problems, conceptually, you could be thinking about the container and what's happening to the container. So the first thing that you need to do with this is realize what kind of container this problem is using. So why does this problem have to be using something like a balloon? Because the volume can change. What about the last problem? Is that also a balloon? It cannot be a balloon because it specifically says that the volume is constant. So that would be more like a aerosol can or a steel container, something that can't change its volume. So when I look at these problems, I'm like, okay, am I thinking about something that is fixed in size, or can it vary? And then what's happening to that container that's filled with gas? I mean, with these pressures that we're doing, absolutely not. I mean, if I jacked it up to thousands of atmospheres, there'd be a minor change that you wouldn't be able to see because the number of significant figures wouldn't even make it apparent. But would it get bigger? At some point, yeah, it would shatter. Right? It would fly apart. Sorry, Jake, go ahead. Yeah, that's exactly what I did. That's all you do. Yeah. I mean, in my calculator, I type 200 times 348 divided by 283 times 550 divided by 860. Doesn't matter because it's multiplication and division, so you can do whichever one you want first, whatever order you want. Just as long as every time I type something that's in the numerator, there's a multiplication sign in front of it, and all these numbers in the denominator, there's a division sign right in front of the number. All right, so So find the volume of this gas of helium whose temperature is 70 degrees Celsius and is at this pressure. Okay, so 70 degrees Celsius, 200 and, oh, I can't really write with that. I'm looking, find the volume. So I'm going to put 0.08206 liters, atmospheres, mole, Kelvin. And why did I write this first? I'm looking for a volume. And so I wrote this first because it gave me a volume unit, because my answer needs to have a volume unit in it. Yep. And there's no liters in the problem, so I need liters. And so I knew this was going to be an ideal gas law problem, because in this problem, it asked me about a volume. It said something about moles, it said something about pressure, and it said something about temperature. So it has all four of the parameters, so that means it must be using the ideal gas law constant. And there's no like P1 and V1 or P2, none of that stuff. So it can't be any of those other gas laws. There's no change in pressure. It's just the actual, in this case, volume. So I'm going to take 343 Kelvin and put that in the numerator. Why? Because I need to cancel that unit out right there, that Kelvin unit out. What else do I got? I have 2.5 ATM. So I'm putting that in the denominator because there's an ATM unit in the numerator that I need to get rid of. What else do I got? So the 3.8 moles goes in the numerator because I need to cancel out this numerator, or sorry, this mole that's in the denominator. And so all the units have been canceled out except for that liters that's highlighted. And so then I can just knock out the math. So 0.08206 times 343 times 3.8 divided by 2.5. And I get 2.96 liters. Say again? This is a 2, sorry. Dang it. That is what I got. Did you have this 3.8 in there as well at the end? This? You got a different number than me? Okay, maybe I screwed up. Just a second. 0.08206 times 343 times 3.8 divided by 2.5. Oh, yep. I typed it into my calculator wrong. So I got 42.8. Okay. Yeah.
How do you decide which way to flip the
What you mean the constant?
Yeah.
What am I looking for in this problem?
volume?
So
That's always got to be.
whatever I'm looking for needs to be in the numerator. So in this case, here are my 4 options, and my problem is going to ask me for either a volume, a pressure, a number of moles, or a temperature. And so if it's asking me for liters, or if it's asking me for volume or pressure, then it gets written like this. And if it's asking me for moles or temperature, then I flip the whole thing over. If I was asking for moles, yeah. What would 50 grams of NO2 gas at? Okay, so this problem I've got a grams, which I can convert into what? Moles. And I've got a pressure and I've got a temperature. So this is another ideal gas law problem, and it's asking me about a volume again. So I'm going to start this off exactly the same way. 0.08206 liters times atmospheres, moles, Kelvin. So Dana, why did I write it like this? Because I need to find volume. So I needed to make sure that I had a volume unit in the numerator where I needed it. And so now my answer will end up having the liters where it's supposed to in the numerator. So now I just need to take everything else that's in this, all the other units that the ideal gas law constant came with, and get rid of them. So 3 units need to be canceled out. So what do you want to cancel out for? Well, before we do this, I should have 273, 163. So what do you want to do first? Sure, I'm going to throw 361K right there, because when it's in the numerator, I can cancel out this denominator temperature unit. Okay, now what? What if I put the 1.54 ATM in the denominator? Why would I do that? Because the ATM unit I need to get rid of is in the numerator, so then those guys get canceled out. So I need to get rid of that mole unit, but I have grams. So I'm going to go ahead and act like the grams can cancel it out by writing 50 grams of NO2 right here. But that 50 grams can't get canceled out by that. It's 15.9994 times 2 plus 14.6. And so what do I need to do next? I need to convert this into moles. So the mass of a nitrogen and 2 oxygens is 46.0014 grams NO2, and that's equal to 1 mole NO2. And so now that I've done that, I can take my grams of NO2 and cancel it out with that gram unit I put in the bottom, and now I can get rid of my mole unit that I needed to get rid of in the beginning. So I'm going to get an answer with liters because that's the only unit that's left, 0.08206. And by that number times 50 divided by 1.54 times 361. So it looks like 3 sig figs, yeah, 20.9 liters. Do we get that? 20.9? Okay. No specific way. I'm not sure what you mean by that. Like the specific way is to just put that unit on the opposite side of the equation. So if it's in the numerator, put it in the denominator, and then they'll cancel. So are you asking, like, do I always put the Kelvin on top?
Well, you don't have to specifically do double first.
Oh, absolutely not. No. You can do whatever you want. If you're doing the multiplication and division on this, the order of operations is immaterial. Totally, it does not matter. So if we would have picked the ATM to do first or the grams to do first, we would have got the same answer. Okay, what this next problem? Which of those gas laws that we talked about? This is Graham's law. So this is the law that's talking about speed of the molecules. And the equation for this one was rate 1, rate 2 equals molar mass 2 divided by molar mass 1. Okay, so I've got CO2 and I've got uranium hexafluoride or uranium 6 fluoride. Which of those two gases is going to be moving faster if they're in the same container? The CO2 is going to be moving a lot faster, right? Because it's a much smaller molecule. And since they're at the same temperature, they've got the same kinetic energy. So to have the same kinetic energy, the littler one must be moving much, much more quickly. So I'm going to take, I'll say rate of my CO2 divided by my rate of my uranium hexafluoride is equal to the square root of 12.011 plus 15.9994 times 2 equals 44.0098 in the denominator, and the numerator, I have no idea. big number. You guys have a like 352, something like that? So 352.0194. Great. 352.04. They're just the numbers off the periodic table for carbon dioxide and uranium-6 fluoride. The atomic masses, yeah. So that top one is a uranium and 6 fluorides, and the bottom one is a carbon and 2 oxygens. Square root 352. And you'll get 352 out of that. Yes. Yeah. So what does this 2.8 mean? 2.8 times faster. So remember, this was a fraction. So this 2.8 applies to the CO2, and a 1 will now apply to the uranium hexafluoride. What I always do is I make sure that I put the smaller number as rate 1. Smaller, the lighter, less massive gas as the first one, which makes me put the smaller number over here, which gives me a number greater than 1. So when I write it like this, it doesn't really matter, but in my head it's easier to think the smaller gas is moving 2.8 times faster than the larger gas, always. If I had done it the opposite, then it's whatever 1 over 2.8 is, which is 0.35 or 0.36. So what does that mean? That means the other gas, the heavier gas, is moving at only 35% as fast as the lighter gas, which is harder for me to think about. So I always like to think about it, this one moving 2.8 times faster. The other way is totally fine, but you just need to be able to explain it. So what's the answer to this question? That the CO2 is moving 2.8 times faster. And the other way to answer this would be that the uranium hexafluoride is moving 0.36 times slower, which is harder to think about for me, at least. What's the net ionic equation for lithium bromide added to a solution of silver perchlorates? Okay, so I've got lithium bromide and I've got silver ClO4 perchlorate. These two things are coming together. And what state are these things in? They got to be aqueous. I said solution, so aqueous. How do you know that the first one is aqueous? Not enough. There's a lithium in the salts. And so the lithium that's in this salt is always going to be soluble, plus the bromine also wants to be soluble. How do I know that the silver perchlorate is also soluble? Because it is a salt. The silver doesn't want to be soluble, but the perchlorate does want to be soluble, and the perchlorate rule is above that. So this guy's soluble. So this is what type of chemical reaction would you say this is? This is a double replacement, so I'm just swapping partners. Which do I swap? The lithium and the silver is what you swap. I cannot attach the lithium to the silver. Why? They're both positively charged. So when I swap these guys out, I'm going to have a lithium that could make a combination with the perchlorate, and I've got a silver that could now make a combination with the bromide. And so now you ask yourself, is this thing going to be aqueous still? It is, because the lithium and the perchlorate want to be soluble. So this guy's aqueous. What about this one? Is this one still aqueous? The silver, remember, doesn't want to be soluble, and the bromine does, but the silver rule is above that. So this is a solid. So I'm just asking you about the net ionic equation in this one. but you kind of have to write out the molecular one or the full ionic to know what's going on. So at the end of my net ionic equation, I'm definitely going to have a silver bromide that was made. So what's the aqueous mean? That molecule's ions, or the molecule itself, is already surrounded by water molecules. So in this case, since we're talking about these salts, that lithium bromide, what has happened to it? It's already been separated. So it's a lithium and a bromide and a silver and a perchlorate and a lithium and a perchlorate and a silver bromide. Solid. So the lithium is the same on both sides, so I'm going to cancel it out as a spectator ion. The perchlorate is the same on both sides of this arrow, so I'm going to cancel them out because they're spectator ions. So what's left is the silver bromide, which I've already written, and then the silver and the bromide. So there's my net ionic equation. That's hard to see because it's really low.
So normally, like, the balance it, you balance it first.
Yeah, and there was no balancing in this one because all the charges were +1 and -1. It depends. You probably don't need to include them in the net ionic. I mean, it's totally possible you might need to. But if these numbers would have been, say, like a 2 and a 2 and a 2, you can just go through and divide through by 2 and get rid of them. But if it was like a 2 and a 3 and a 4, then you'd need all of them. Okay.